with 5 marked points and 4 examples of curves, which I just drew just to kind of illustrate this idea that what's important about the curve is the boundary segment where it starts, the boundary segment where it ends. And so these 2 curves count as the same, for example. Right, so there we go. I haven't told you anything about what I'm doing with the curves just yet. I'm thinking about the set of all the curves for now. And then what I'm going to do is I'm going to write down a bunch of equations. And so the equations are right there. So one equation for each curve, gamma. So the equation says u gamma plus the product over everybody that crosses, all the deltas that cross gamma, those 2 things together are supposed to sum to 1. And we're interested in trying to solve these equations. The C gamma delta is the minimum number of intersections between 2 curves. So if you have, and in the disk, that's going to always be 0 or 1. So all we're getting is a u gamma plus some square free monomial that captures the curves that cross gamma. Those 2 things together are supposed to sum to 1. So if we look, for example, when n is 4, so we have these 4 boundary segments. If we look at the u1, so that's the equation corresponding to this curve. We get u13 plus the product of all the curves that cross the 1,3 curve. There's only one. It's u24. So we get u13 plus u24 equals 1. If we look for the u24 curve, we get u24 plus u13 equals 1. And if we look at the curves for the short guys like 1, 2, well, we realize that nobody crosses them. So we get u12 plus 1, the empty product, equals 1. So the short curves are just automatically going to be set to 0 to solve these equations. And so I'm frequently just going to forget about them entirely because they're just fixed by the equations. So the interesting thing that we can already see a kind of interesting thing here, which is we had 6 variables and we had 6 equations. And so just naively, we might have expected that the solutions would be just a bunch of points. But that's not what happened. In this case, because we had 2 equations that were actually just the same, we got a one-dimensional family of solutions. So here are the equations again, just to recall them. We're going to be interested in solving the equations. So I'm going to write u for the solutions over the complex numbers. I'm going to write u sub greater than or equal to 0, which I'm going to call the totally non-negative part of u, for the solutions where all the u's are non-negative. And that's really going to be the thing that we're going to be particularly interested in understanding. And so to begin with, to get some kind of sense of what is this space going to look like, we'd like to think about its boundaries. So boundaries are going to be where some u gamma equals 0. So a first thing that I want to notice is that if all my u gammas are non-negative, and I look at some equation like this, which says u gamma plus a product of some other u's equals 1, then in fact, both of these terms are going to be non-negative. And that implies that u gamma had better be between 0 and 1. So that then this product will also be, and this product will also be between 0 and 1. Okay. So again, suppose u gamma is 0, and let's think about what happens for any delta that crosses gamma. Well, so we have the u delta equation, which says u delta plus a product of a bunch of u alphas equals 1. But u gamma appears here because delta and gamma cross. And we said that u gamma is 0. So this product is 0. So as soon as we know that u gamma is 0, we actually know that u delta is 1 for any delta that crosses gamma. So that means something really nice is going to happen to the solutions where u gamma is 0. What we should do graphically is we should think about taking our disk on which we have some curve gamma, and we should think about cutting it along gamma. And once we do that, we have 2 smaller disks with marked points. And the reason we should do this is that the curves that cross between the two components are all equal to 1. So in the products, who cares? They're not going to play any role. So in fact, what's going to happen is that the equations for the remaining variables, are either live in the first component or in the second component, and the equations relating them are just exactly the equations that come from these two smaller pieces. And so we say the boundaries of the totally non-negative part factorize. And in fact, this exact kind of factorization is familiar if you've ever looked at associahedra or M0n bar, you've seen exactly this kind of factorization before. And so this factorization was the motivation for Koba and Nielsen in 1969, for physicists, to write down these equations to define this totally non-negative part of U. And their purpose was to define something that's now called the tree string amplitude. And so the way the tree string amplitude works is it's a function of some variables associated with the curves. You can think of them, I mean, slightly loosely, as being momenta of particles. And so the goal is to describe some scattering process. So you have some particles that are coming in together, they're going to interact, they're going to zoom off again. You want to describe that by describing this function, this amplitude function, and the data that you have are these momenta. Technically, not exactly momenta, but anyway, these so-called Mandelstam variables. And so the way it's defined is it's an integral over the totally non-negative part of U gamma to the power P gamma, where these P gammas are the Mandelstams, and the U gammas are the solutions to the U equations. Oh. The tree, yeah, because this is the tree string amplitude. I'll say a little bit more about what that means just in a moment. No, it's not obvious, but I don't want to try to tell you. Sorry. Yeah, it will be easier to write down the measure with some of the things that I've developed by the end of the talk. And so if you ask me then, I can say what the measure is. So the point is that if some particular P gamma goes to 0, then for physics reasons, the purpose, the goal, I mean, you want to write down the goal of the physicist was to write down a function that would have the property that if some P gamma goes to 0, then the amplitude would factorize as the product of two smaller amplitudes, exactly as we described is happening for U greater than or equal to 0. And that's guaranteed by the factorization that we saw, because what happens when P gamma goes to 0 is that the part of the integral that so the integral gets concentrated towards where U gamma is 0. So the factorization produces the factorization of these amplitudes, which is exactly what you want. It's what the property of the amplitudes are supposed to have. Okay. So to work with this, we want to get a better handle on solving the U equations, and I will say more about that. But before I do that, I want to sort of explain a little bit about the physics motivation, because I find it, appealing. So in perturbative quantum field theory, the tree amplitude, the one we've been discussing, is just the first, or really the 0th term in some series of corrections. So the 0th term is like the first term, and then the 0th term, and then you have these successive terms that are further corrections to that initial term. So these higher order terms should be obtained by using similar notions, but applied to surfaces of higher genus. So already in 1969, people were aware that that would be the right thing to do. So after Koba and Nielsen had written down this thing for the disk, people knew that was like the next thing to do, is think about these other higher genus surfaces. But at the time, nobody really could figure out how to make any progress on that. It turns out that the approach that I'm going to be describing is able to handle those higher genus surfaces. And well, so the physics part is not finished. The solving new equations part we can do for the higher genus surfaces. I will explain how that works. Okay. So we are now on to, okay, I've discovered that there is no way for me to tell what number of slide I'm on. So that'll be exciting. Well, we'll see what happens. Okay. So we're now going to get into the representation theory part, which, as I said, I want to go into because I think it's beautiful and worth being at least enough acquainted with, that if something comes up that really is quivers, that you would be able to recognize it and go, oh, that looks like quivers. So a quiver, we go shoot. Hello. It's much more reluctant to go backwards than forwards. Thank you. That makes it work. Thank you. Awesome. Okay, thanks. So, right. So quiver is just a finite directed graph. I should say, so I was really excited when I found that out, because like while I was a grad student, I'd heard people talking about quivers and I was like, oh, this sounds like it must be some like complicated thing that, you know, only like smart people would understand. And so I was very pleased when I found out it was just a directed graph. And so I was enthusing about this when giving a talk at an AMS sectional. John Stembridge was in the audience. And when I said, a quiver is a finite directed graph, he stuck up his hand. I was like, uh-oh. He said, a quiver is a finite directed graph with pretensions. So there you have it. So a representation of a quiver is an assignment of a vector space to each vertex over some ground field, vector space to each vertex, and a linear map between the corresponding vector spaces. In my examples, I'm just working with C. No particular reason. So in this example, we have 3 vertices, 2 arrows, and I just chose to put a one-dimensional vector space and then a two-dimensional vector space and then a one-dimensional vector space. And so then I had to tell you some linear map from a one-dimensional vector space to a two-dimensional vector space, and a linear map here from a two-dimensional vector space to a one-dimensional vector space. Fine. Which I did just by specifying a matrix. And here, you know, there was just one vertex and an arrow that was a loop. So that corresponds to, so I need a map that goes from this two-dimensional vector space back to itself. So that's those are representations of those two quivers. Two representations are isomorphic if you can obtain one from the other just by changing bases. So one important example to bear in mind is that for this little quiver with 2 vertices and 1 arrow, these are all isomorphic provided alpha is non-zero, because by changing, in this case, by changing bases at either vertex, in fact, I can change alpha to whatever non-zero value I like. But if I would have taken alpha 0, that's not isomorphic. It's not equivalent. So the direct sum of 2 representations is just obtained. You take the direct sum of the vector spaces. And then you just define the maps so that they respect the direct sum decomposition. A representation is indecomposable if it's not isomorphic to a direct sum of two smaller representations. So the indecomposable representations of this two vertex one arrow quiver are as follows. You could have a one-dimensional vector space and a zero-dimensional vector space, or a zero-dimensional vector space and a one-dimensional vector space, or two one-dimensional vector space and a non-zero scalar. If I would put a zero scalar, that's not indecomposable, because with zero there, I can write that as the direct sum of this guy plus this guy. But with a non-zero guy, he becomes indecomposable. You can't split him as a direct sum. So what theorem in first year linear algebra is this statement that these are the three indecomposable representations of this quiver? Anyone? Yes. Yeah. I mean, so, whoa, what happened? Oh, phooey, right. So it's here. So it amounts to saying that optimal multiplication on the left and right by invertible matrices, any matrix is equivalent to a partial identity matrix like this. I mean, just to say it very explicitly, because this matrix defines a particular representation, like to specify a representation of that two vertex one arrow quiver, you just need to specify one matrix. And then when you split it apart into pieces, you find k copies of the C goes to C map, and n minus k and m minus k copies of the other two indecomposables. Okay. So a morphism between two representations, I also need to define. It's just a collection of linear maps. Oh, and this is really a slide where if you haven't seen this before, don't worry about it. You know, if I'm, you're not surprised. I defined an algebraic object. I'm also going to define morphisms between them. So don't be surprised. And don't worry too much about what it says, because it's some definition of morphisms. Anyway, so it says that some triangles have to commute that relate. So the morphisms are linear maps between the corresponding vector spaces, and they have to satisfy some commutation relation. Okay. So let Q be some orientation of a path. So something like that. And we're starting to sneak up on things that were in Mohan's talk. The indecomposable representations are easy to describe. They're just described by taking a connected subset of the vertices, putting one copy of the field at each of the guys in the subset. So here I chose these three, put a copy of C at each of them, and putting non-zero scalars on the corresponding arrows, putting zeros everywhere else. That defines a representation. It's pretty easy to convince yourself that that representation is indecomposable. It's not so easy to convince yourself, I mean, it's not super hard, but it's not so easy to convince yourself that those are the only indecomposable representations. But it's true. I should mention that this is very special to these orientations of a path. As soon as you have a vertex of degree 3, then you have more interesting representations. They're not going to come up in what I'm talking about today. So I'm not going to discuss that, but anyway, I don't want to give you the impression that every quiver representation, every indecomposable quiver representation looks like this. But for the quivers that we're going to be interested in, that will be true. So what's the connection to the problem we started with? Well, fix a triangulation of the disk such that every triangle includes at least one boundary edge. So here I'm drawing a triangulation, and now I'm really drawing a triangulation using the marked points that I started with. So I have these marked points that were there from the beginning, and I'm using them to divide the disk up into triangles. And I'm just insisting that every triangle include a boundary edge. So this guy has a boundary edge. This guy has two boundary edges. That's fine. But I want everybody to have at least one boundary edge. In fact, for experts, this would all work fine if I didn't do that. But some of the combinatorics would be less easy to work with. So I'm putting this assumption because it makes life easier and more prettier. So what we're going to do from this triangulation is we're going to define a quiver where we put a vertex on each of the diagonals, the internal edges of the triangulation. And we connect them by putting an arrow between two vertices if you have two consecutive vertices, like here, here we have two consecutive diagonals meeting at this point. And so we put an arrow between the corresponding vertices. And here we have two consecutive arrows. And so we put an arrow between the corresponding vertices. So, and it turns out that under the assumption that I made that every triangle has at least one boundary edge, this quiver will be an orientation of a path. So what we want to do is we want to turn our geometric data of curves on the surface into indecomposable representations of Q. And roughly the way we want to do that is to say, is to consider the set of diagonals crossed by the curve gamma, which is some consecutive set of vertices of Q. And as we said, that defines an indecomposable representation of Q. That isn't exactly right. That isn't exactly what I want to do. If we think about it for a moment, we realize that the number of curves, and here I've forgotten about the very short curves. So I've already removed the very short curves because they're not interesting. They're not going to show up in the representation theory. But the number of, once I've done that, the number that I have left is n times n minus 3 over 2. But the number of indecomposable representations of the quiver is less than that. So we need extra objects. For people who are a little used to this situation, to this general setting, that might not seem like such a surprise, because it's exactly what you see in cluster algebras. When you're categorifying cluster algebras, you need those well, whatever the rank is of your situation, you need to add that many extra objects. And typically they get described as shifted projective modules. And to give them that a precise meaning is well, really outside the scope of what I need to talk about. So for us today, we're just going to think that there's some extra formal objects, and I'm really going to blur the distinction between them and the regular modules. But so the point is that once we sneakily add these extra representation theoretic objects, then we have a perfect correspondence between curves on the surface and modules, where among my modules I'm including these extra guys. Okay. So to explain why this is useful, I need to introduce, and I want to introduce, another piece of quiver technology, which is the so-called Auslander-Ruyten quiver. And one of the reasons I want to introduce it, aside from the fact that it's useful, is I also think it's extremely beautiful. And so I want to tell you. So this is a directed graph whose vertex set, whose vertex set is the indecomposable representations, and whose arrows are given by what are called irreducible morphisms. So those are certain special morphisms that don't factor through any other modules. So for example, for this quiver here, so so these are the indecomposable modules, and you can see that there's one for each possible way of choosing a subset, and I've sort of compressed things I didn't write in the arrows because the arrows don't actually carry any information. So these are the indecomposable modules, and this is the Auslander-Ruyten quiver. So there's a simple combinatorial procedure for constructing this quiver for a quiver Q with in fact it's a lovely process. Anybody who is intrigued, I'm happy to explain it afterwards. This gives you a way just to write down the root system for E8, for example, because if you do this for E8, then you will see all the indecomposable representations for E8, which are in bijection with the positive roots. So it just, you can write them down as fast as you can write. You can just list them off, which I find really cool. I don't need to look at the back of Bourbaki anymore. I can just write them down if I need to see them. So as I said, simple procedure. And in type A, it always has this kind of grid-like structure, which is maybe a little bit obscured in this picture because it's too small. So an important feature, I'll have a bigger example in a moment. Another important feature of the Auslander-Ruyten quiver is what's called Auslander-Ruyten transformation or Auslander-Ruyten translation, which sends each indecomposable to the next one over to the left. And as you might imagine, there is a more conceptual way to describe what the Auslander-Ruyten translation is doing than move everybody one step to the left. But it's actually a little bit complicated. And so I don't want to get into it. Just, if we're willing to sort of grant that this is an interesting looking picture, then you might believe that there's something to be said about, just the operation of moving everybody one step to the left. One reason it's interesting is that the guys on the left-hand end are the indecomposable projective modules, and so they are behaving differently. And in particular, their Auslander-Ruyten translation will be 0. And let me just say, the guys on the other end are the indecomposable injective modules. And in this setting, unlike most settings, there's a complete duality between projective and injective, and so they behave exactly the same way, which makes our lives easier. So, equipped with some kind of understanding of the Auslander-Ruyten translation, we can describe the intersection number in representation theoretic terms. So my goal here, if this wasn't clear, is I want to take this picture of drawing curves on a surface, which is something that I don't feel like I understand very well, and I would like to turn it into algebra, which I will be happier about. So in order to do that, first I needed some objects that would represent the curves. Secondly, I needed to understand what it means for curves to cross. It turns out that the crossing of two curves is the dimension of the morphisms from m gamma to tau m delta, plus the dimension of the morphisms from m delta to tau m gamma. Where, again, these m gammas are the representations corresponding to the curve gamma, and I'm sweeping under the rug the fact that m gamma might not be a completely honest representation. So this means that at this point, we have a completely algebraic version of the U equations. And it's also interesting to see this in the Auslander-Ruyten quiver. Oh gosh, it's really not very visible, is it? So what I was trying to draw here is this is my m gamma, and then we're supposed to look at where in the Auslander-Ruyten quiver are the vertices that correspond to things that cross it. And it turns out that can be described as sort of two partial rectangles. You start here, you go one step to the left, and then you start drawing a rectangle that starts there and goes up and down as far as possible. And so you get this region. And you do the same thing over on the right, and you get this region. Okay. So I need one more ingredient to describe a representation theoretic expression for the solution to the U equations. So that's where we're going with this. We didn't just want to write down the U equations algebraically. We really wanted to be able to solve them using the algebra. So there's one further ingredient that I need. So if M is a representation, well, to begin with, what I need is a notion of a sub-representation. So this amounts to choosing for each vector space that makes up my representation, I'm going to choose a subspace, but I'm not going to do it in an arbitrary way. I'm going to do it in such a way that for each arrow in the quiver, the map corresponding to the arrow should take the subspace here to the subspace there. And more explicitly, if Q is an orientation of a path, the case that we're kind of focusing on, we can view M as defining a fence poset. And then subrepresentations are nothing but order ideals in that poset. So, oh, thank you. Yes. Yeah. So for example, let's let this be M. We can look at the subrepresentations. So we can take nobody at all. That's a perfectly good subrepresentation. We could put a one-dimensional vector space. We could choose the one-dimensional vector space here and 0 there and there. That's a perfectly good subrepresentation. That's him. I could take a one-dimensional subspace here, but if I do, I'm forced to take the one here as well, because the image of this guy is supposed to also be in the subrepresentation. So I have this, but I don't, for example, have one where I would just have this C, but I would have 0 there. So I can have this, I can have this, where I took the C on the left-hand side, or I could take both of them. And so those 5 possibilities are just the 5 order ideals in the fence poset that corresponds to M. And we're going to need something that is very close to the rank polynomial. It's a little bit more refined. What I want to do, if I have a subrepresentation, I want to write y to the power of dim n for the product over all the vertices that appear in the subrepresentation of yi. So if we were just looking for the F polynomial is going to be the sum over all subrepresentations of these y to the dim n's. So I'm taking these sums of monomials in the y's. If I were to set all the yi's equal to t, that would be exactly the rank polynomial. But I want to remember the different y's, and so this is what I do. Okay, so this is the F polynomial. So these, I mean, it's a natural notion as a way to measure somehow the subrepresentations of a representation, but it was introduced not really that long ago by Dirksen, Wayman, and Zelevinsky in their study of quiver representations applied to cluster algebras. And I should say about this that this formula, in writing the formula like this, I'm kind of cheating a little, because here for this representation, for the representations coming from a path, life is sort of simple. And if I pick out a particular dimension vector of a subrepresentation, either it is a possible dimension vector of a subrepresentation, either it is a subrepresentation or it isn't. But in general, life can be more complicated. There could be different subrepresentations with a given dimension vector. I mean, that's going to start happening. If this dimension at the middle vertex were not 1, I mean, in general, if M was some representation which was not indecomposable, we could still think about an F polynomial for it, but we would then start to realize that, oh, we can have subrepresentations we can have multiple subrepresentations appearing, and in fact, we have those subrepresentations are not some finite number of them. They're actually coming in moduli spaces. So you have to count them in a more sophisticated way. You can't just do what we did here, which really was just a matter of counting them because there's only ever 0 or 1, so we can just count them. You have to count them using an Euler characteristic of the corresponding quiver Grassmannian. Anyway, for experts, don't worry about it. So using these F polynomials, we can describe our solution to the U equations. So they are as follows. We just set U gamma to be 1. So to begin with, I'm going to describe the U gammas as rational functions in y1 through yn, and then we can imagine specifying, specializing y1 to yn to positive real numbers, and those will give us solutions in the totally non-negative part of U. So what's the solution? It's just U gamma is 1 minus y to the dimension of m gamma divided by the f polynomial for the tau of m gamma and divided by the f polynomial for m of gamma. And it turns out there's another way to write it, which is just as a ratio of f polynomials. So here E1 and E2 are given by the little mesh, so-called, that you see in the diagram, where you look in the Alexander-Ruyten quiver, you have the m gamma, and then you have, remember, tau moves things one step to the left. This is tau of m gamma. And then it's a feature of this quiver. Well, as I said, in the case of type A, there are these little meshes that look like diamonds. In fact, it's a general phenomenon, though they can be a little more complicated. But the quiver is made up of little meshes. And so what I'm really doing here is taking the guys these two guys at these two corners of a little mesh and taking their product. So this gives us two different expressions for U gamma, which happen to be the same. And the fact that they're the same is actually a key, very super crucial key ingredient of the proof. And it holds for any finite dimensional algebra by a result of Dominguez and Geis. And here are just a few little bonus facts for people who are really trying to keep track of the fact that, m gamma might not be a real representation. What are we supposed to do then? Well, so if you are one of these funny shifted projectives, your f polynomial is just 1. So that's easy. Your dimension is just 0. And the Alexander-Ruyten translation of the shifted projective is just the corresponding injective module, which means that the shifted projectives actually go on the far right-hand side of the Alexander-Ruyten quiver just after the injective modules. Okay. Okay, so I want to, it's always a little bit dangerous to even try to think about proving anything, but in a talk. But I wanted to give a tiny hint of the proof because there's something cool and I hope perhaps visible in the proof and you can sort of see how things are going on in the Alexander-Ruyten quiver. So here's an example. Here's an example that we saw before of an Alexander-Ruyten quiver. So this is some quiver with 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. And so this is the Alexander-Ruyten quiver. And the U equation corresponding to this module was U gamma plus the product of all these guys in orange and those guys in orange is supposed to equal 1. And so the key point that I wanted to make that kind of explains how it all works is that it's a telescoping argument. So we had this description with U deltas over here as ratios so that the U delta associated to this guy is a ratio of 4 guys. And then the U delta associated to this guy is a ratio of these 4 guys. And U delta associated to this guy is a ratio of those 4 guys. And you start to see that when you multiply those all together, there will be massive cancellation and almost everything goes away. And that's pretty much the proof, in fact. So that's the so that describes the solution to the U equations in the case of the disk. And now I want to say a little bit about the more general versions of this. So one thing you can do is everything that I said in terms of the algebra works pretty much the same way for any finite dimensional algebra, provided it has finitely many indecomposable modules. So here we've forgotten about the idea of surfaces. Surfaces are not in the picture. We're just taking an algebra that has finitely many indecomposable modules. And we know how to write down U equations for that. We don't really know what they might mean, but we know how to write down U equations and we can find solutions to them. The argument, the Alexander-Ruyten quiver doesn't quite look the same, so the argument is sort of less beautiful and explicit, but it still telescopes. And so we still get the solutions to the U equations described in exactly the same way. one thing I should say is that we can't rule out the possibility that there are other components in this case. I mean, we don't think it happens. We know it doesn't happen in type A for other reasons. In the surface case, in the disk case, we know it doesn't happen. But in all the other cases, we don't actually know it doesn't happen. There could conceivably be other components. We don't think that happens. But anyway, this generalization is related to, for example, the quivers look like this, these grid quivers. So these happen to be, once I impose some relation, so this is, anyway, so whenever you have, where these little dotted lines are, that represents the fact that the corresponding composition of two arrows is supposed to be 0. Anyway, so these guys, such quivers, these grid quivers, have the property that there are only finitely many indecomposables. And the solutions to U equations in this case are related to the physics of Cacciazzo, Early, Guevara, Misera scattering. And I'm working the details of that out with Nick Early. So that's sort of a slightly different direction. Well, not really that different, I guess. For other unpunctured surfaces, instead of getting the quiver of type A, you get some gentle algebra. And the idea that there's some translation between surfaces and gentle algebras is an idea that's been, that a number of representation theorists have been exploiting over the past, I don't know, 8 years or so. Palu, Pilot, Plamondon is kind of like the most relevant for what we do, but there's other people who are doing similar things. And so the problem from our point of view with these algebras is that they have infinitely many indecomposable modules. And that introduces some complications, which I just decided that for the purposes of giving this talk, I was just not going to focus on. So I mean, the issue is that we have these products in the U equations, and they're not going to be well defined. What it turns out you can do is that at least, well, you can sort of group together modules into equivalence classes of modules, and you can still write down some U equations, and you can solve the U equations in much the same way. And so this is, this then provides us with solutions for these other surfaces, the U equations, and my physicist friends working on this project are investigating the process of using that as input into their string theoretic goals. For punctured surfaces, the algebras are not gentle, they're only locally gentle, and we think we know how it all works, but there's some details to work out. Some of our representations are infinite dimensional, and that means that the F polynomials become formal power series. So I wanted to mention that since we are at FIPSAC. Anyway, but yeah, so this is a little bit more complicated, but should also work. There's also something which I'm really interested in, which is U equations associated with any finite dimensional algebra, where we have this same problem as before, that we now have infinitely many indecomposable modules, and potentially, this one could hope for this for algebras that are called wild, which means that understanding those families of indecomposable modules is hard, much harder than it is for gentle algebras, which are so-called tame, and so the sort of families of modules are kind of well understood. This means that, so for these wild finite dimensional algebras, we don't really know how to, well, we have some guesses about how one might group modules together and then write down some U equations, but we certainly have zero idea about how to solve those. And I am eager for input from anybody who has thoughts about that. Okay, so just to summarize, what I did was today was to describe a way to reformulate the U equations, really just for a disk, but with the idea in mind that this would also work for other surfaces. And we expect that being able to do this for other surfaces. So the disk case was not new. The disk case was understood by Koba and Nielsen in 1969, but we expect that being able to do this for other surfaces will really have consequences in string theory. So thank you very much.
Thank you. Any questions?
Hey, thanks for the great talk. Can you tell me about how you group representation together in the infinite case? You said that there are infinitely many indecomposables here for this surface, but we group them together. How do you do that?
Okay, so in fact, I was maybe a little bit vague about that. I'm not going to group them together, or even after I group them together, there are still going to be infinitely many, but there's going to be a reasonable infinitely many. What I'm going to do is I'm going to look at so there's going to be infinitely many tubes, and I want to group together all the guys at the bottoms of the tubes and say, those guys, they differ only by, what I did with some, they differ by some continuous moduli. That's not so interesting for my purposes. They all look the same. I'm going to group them together. And I'm going to group together the guys on level 2 of the tubes and level 3 of the tubes and so forth. But I'm still going to keep the infinitely many pre-projective and the infinitely many pre-injective modules because there's no sensible way to group them together. But so that means that the products are still going to be infinite products. And so to think about those products, we have to think about the convergence of those products as convergence of formal power series. And you can prove that you can see that as formal power series, up to any particular degree, only finitely many terms in the product will contribute. And so that means that the product is really well defined as a formal power series. And it's in that sense as formal power series that we're able to solve these things for gentle algebras. Of course, the physicists then just want to stick in numbers for the y's regardless of, because they're like that. But
Oh yeah, and there is a question from the chat. Patricia Klein asked, is there a relation between the Auslander-Rayton quiver and the Auslander-Rayton conjecture?
I don't know what the Auslander-Rayton conjecture is. I'm sorry.
Any other questions?
I have a question about your slide where you had a grid.
Yeah. Oh, this one?
Yeah.
Yeah.
What do you mean quivers with relations of the form?
Yes. So I didn't. Sorry, that was something which I didn't really take time to explain. So the quiver here is just this sort of grid where I have arrows going up and arrows going to the right. And one can talk about relations of that quiver, but I want a subcategory of the relations of that quiver in which I require that whenever I have like these dotted lines, which correspond to, so each time I have these dotted lines, that corresponds to some pair of arrows that are composable. So like this arrow can be followed by this arrow. What I want to insist on is that when I choose the matrices that correspond to these arrows, that product should be 0. So that's a subcategory of the category of all representations of this quiver. And if I was going to think about the category of all representations of this quiver with no relations, it would be badly infinite. It would be out of hand. But if I impose all these compositions are 0, then it turns out there are only finitely many indecomposable representations.
Yeah, that was my confusion. Why did you say that there were finitely many indecomposable?
Okay, yeah, so it's because of that. Okay, good.
Thanks.
You're welcome.
Oh yeah, Patricia unmuted it, so she's gonna ask a question, follow-up question.
What?
Please go ahead.
Sorry, I just had the question about Gauss-Lambda rate and conjecture, but it's maybe there's no relation. It's fine.
Well, I'm not sure what conjecture you're.
Right. I didn't mean to ask again. I just meant to ask the ones in the chat. Sorry.
Oh, okay, that's fine. Anyway, yeah, we can talk about it another time if you like.
I have a question too. So it seems in a lot of the examples that you're giving, you have your arrows directed in a way there's a general flow,
Yeah.
maybe a unique minimal, unique maximal element kind of thing. So do things break down when you have a random choice of orientation on each edge?
No. That was I guess a poor choice on my part if I to have only so in this case the quiver that we're looking at is the so the quiver that you started with is the opposite to the quiver that the quiver structure on the projective. So anyway, so the point is that this is this complicated thing where you have like here the arrows were going. So the arrow, if you want to think about the quiver, the arrows are going, so starting from the top, the arrows would be going like that and 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 like that. So it really doesn't depend on a nice choice of things. Was that the orientation, the orientedness that you were thinking of, Sarah?
Actually, I was hoping that something does break down when you have maybe cycles or something in there.
Oh, well, cycles. So if the quiver itself had cycles, then things get a lot more complicated. Well, so let me say the following thing, just because it's a lovely thing, and I sort of wanted to say it, and I haven't had a chance to say it yet, which is, for which quivers do we only have finitely many indecomposable representations? So it's Gabriel's theorem says that they are exactly the simply laced Dynkin orientations of simply laced Dynkin diagrams. So those are the ones where you're going to see a beautiful picture like these pictures, like these pictures here, where there's sort of a left-hand end and a right-hand end, and things are going from left to right. And as soon as you have something that's not a Dynkin diagram, then you're going to have infinitely many indecomposables, and there's going to be multiple components to this quiver, and all kinds of things will break down in various ways. So I hope that's enough of a breakdown for you. Super.
Okay. So when you're solving the equation, you find that these like short arcs that don't have any crossings with other arcs turn out to be 0. Is there like a deformation of this equation where those play a non-trivial role, or like an algebraic story?
No, I mean they're just 0. So yeah.
Okay, thanks.
You promised to say something about the measure in the integral.
I did promise to say something about the measure in the integral. Yes. Is there an eraser? Oh well. So the integral, if we write it in terms of the y's, then we can write the measure very easily. So recall that the integrand, as I wrote it, was u gamma to the power of p gamma, well, product over all the gammas. This is an integral over u greater than or equal to 0. Then the measure turns out to be just dy1 over y1, dyn over yn.
Okay, if you have more questions, then you can use coffee break. So let's thank Hugh again for his wonderful talk.